have been looking at chromatographic separation in the past few lectures. Chromatography is the most important downstream purification step. The main advantage of chromatography is it can be used for small molecules, metabolites, biomolecules like proteins, peptides. That is why a lot of time is spent in taking this chromatography. There are different types of chromatography. We talked about ion exchange chromatography, we talked about gel permeation chromatography, we talked about reverse phase or hydrophobic interaction chromatography, and recently I started talking about the affinity chromatography. So affinity chromatography is looking at a affinity between a ligand and a protein. That means a biomolecule recognizes another target molecule complementary in shape and size. So you have a protein, antibody, a ligand and an enzyme and so on actually. So either the protein can be immobilized on the stationary phase or the ligand can be immobilized on the stationary phase. So it tries to capture whatever is complementary to it, both with respect to the shape and size. So affinity chromatography is the most perfect chromatography in all these techniques, which is very selective, unlike the other type of chromatography. That is why affinity chromatography is very expensive tool, and it is used in highly expensive biomolecule separation, maybe pharmaceutical products and so on. It cannot be used for normal bulk chemicals because the cost of affinity chromatography is very high, and it is very exact type of technique. So we saw this picture in the previous class as well. So what you have is you have a inert support here, we have the affinity ligand anchored to this inert support. Now imagine we have a mixture that needs to be separated. We have those molecules which are complementary to this affinity ligand and those molecules which are not complementary to the affinity ligand. So what happens as the mixture flows here, those molecules which are complementary to the affinity ligand get bound and the remaining molecules flow out. Okay, so we are separating those which are complementary and those which are not complementary. And how do you later on separate those which are bound? We can change the pH, we can change the buffer conditions, we can change the hydrophobicity, thereby desorbing those molecules which are bound to the affinity ligand. So this can be used very selectively for capturing only those proteins which you are interested in. So if you have ligands which are inhibitors to those proteins, those ligands could be anchored here and those proteins will bind, remaining proteins will just travel through because they are not complementary. So we have concentrated our desired protein. This is how the affinity chromatography works actually. So let us look at more about the affinity chromatography. So we have the affinity ligand, but then there is also something called a spacer arm. You need a long spacer arm so that the protein is bound only to the ligand, it does not have any interaction with the matrix. If it has an interaction with the matrix, sometimes if it's the protein may get deactivated or denatured, so we do not want that to happen. So we have a very long spacer arm, maybe a long chain hydrocarbon, and at the end of this chain you may have the ligand fixed here. Now the ligand interacts with the protein through a specific binding site. So as you know, all proteins have a binding site whose shape and size matches exactly with the ligand. So the binding could be between an antigen and an antibody. So you see it becomes very specific and no other antibody will bind to this antigen. You can have a substrate or a inhibitor or a cofactor binding to an enzyme. So the substrate could be very specific to the enzyme, other enzymes will not bind to this substrate. It could be a regulatory protein to a cell surface receptor. So the protein and the cell surface receptor are complementary to each other. So this is how you achieve this specificity in the affinity chromatography. So any component can be used as a ligand to purify its complement binding partner. So enzyme means it could have a substrate analog, it could have an inhibitor, it could be a cofactor. If it is an antibody means it could be an antigen, it could be a virus, it could be a cell. So if I am going to separate a virus present in a mixture, I run through an affinity chromatography where the antibody is my affinity ligand. So only that particular virus will get captured by this antibody. So I want to purify here a material, intracellular material, but I want to remove the virus. So we can use an affinity chromatography. You can have a lectin, you can have a polysaccharide or glycoprotein or cell surface receptor or cell. If you have a nucleic acid, we can have a complementary base sequence, histones, nucleic acid polymerase, nucleic acid binding protein and so on. So if you have a hormone or a vitamin, we can have a receptor or we can have a carrier protein. So complementary type of systems. If you have a glutathione, you can have a glutathione S transferase, which is exactly complementary to glutathione, or we can have a glutathione S transferase fusion proteins which are again complementary to glutathione. So the glutathione could be bound to the stationary phase and we can selectively capture these type of enzymes. If you have metal ions, we can have poly-his fusion proteins, we can have native proteins with histidine, cysteine and so on. So if you have tryptophan residues on their surfaces. So all these types of complementing systems could be considered for purification. So once you have captured these proteins or viruses, now how do you disrupt this ligand protein interaction, because you need to reactivate the column. How do you do that? We can change to acidic conditions, like we can bring down the pH to 2 to 4. So generally this type of approach is used if you want to separate protein and antibody ligand affinity. We can increase the ionic strength, okay. For example, in the case of heparin, by increasing the ionic strength, heparin which is bound can be liberated. You can use specific eluents. For example, we can have immobilized ligand, that means the ligand which is immobilized also in the effluent, or we can have analog in the free solution, that means we can have a similar looking protein which will displace the original protein which is bound to the affinity ligand. So all these techniques can be used for desorbing or disrupting the ligand and protein interaction. So for example, we have the affinity ligand here with the spacer arm. Now there is a protein which is now adsorbed. Now if you want to desorb, we have to change the environment. So the Kd values suitable for elution generally between 10 power minus 1 to 10 power minus 2. In that situation you can desorb this protein which is bound to the affinity ligand. Or we can also have the same affinity ligand which is in the matrix bound form in the free form or in the eluent. So what happens, the protein which is bound now will get unbound and then it will bind to this free form of the affinity ligand. So it is like a displacement. So the protein which is bound will get unbound and then it will bind to the free form of the affinity ligand which is flowing down through the column. So it is like a displacement type of approach. So this is another technique by which we can desorb whatever protein that has been adsorbed on the affinity ligand. Another approach, we can have analog protein which is almost similar to the protein that is bound. So what happens, this analog protein displaces and the original bound protein goes into the free form. So for example, elution of his tagged protein from high trap chelating by adding imidazole. So we add imidazole, so whatever his tagged protein that is bound gets displaced. So that is another approach. So we see so many different approaches. We can change the pH, we can have a protein which is analogous to the original protein, we can have this ligand which is immobilized in the free form, we can change the salt concentration. So by doing all these we are disrupting whatever has been adsorbed from the adsorbed state into the free form. So the interaction between the target molecule and an affinity ligand is always a reversible process and it is an equilibrium process. So there is something called a dissociation constant. So if L is the free ligand, P is the protein, it forms a complex called LP and this is a reversible reaction, okay. And this equilibrium dissociation constant is called Kd. If Kd is very small, then the binding is very strong. So if the Kd is very large, binding is very weak, okay. So smaller the Kd, stronger is the binding. So good binding if you want to achieve, generally Kd should be in the range of 10 power minus 4 to 10 power minus 6. So if the values are greater than 10 power minus 4, then you are going to have weak binding and the target molecule may leak as a dilute broad zone. That means the binding is not going to be very strong and the target molecule will slowly start leaking out. That is called leaking during sample loading, and they start getting washed actually. So the best values of Kd should be in the range of 10 power minus 4 10 power minus 6. So we can do a small experiment in the lab, we can take the affinity ligand, immobilize it, and then we can run some simple batch protein experiments and then see what is the dissociation constant, and then from the dissociation constant we can tell whether the binding is going to be strong or whether the binding is going to be weak. And generally, as mentioned here, we would like to have a Kd value between 10 power minus 4 to 10 power minus 6. So if you have 10 power minus 4, obviously the binding is going to be weak, and if it is around 10 power minus 6, the binding is going to be strong. So how do you modify these Kd values? It can be modified by changing conditions, as mentioned before. We talked about changing the conditions, okay. So initially you want a good binding because you are trying to capture the protein. Later on you change the environment so that whatever has been captured is dissolved. So that means you are modifying the Kd value. But one big problem you need to consider is if the ligand binds too strongly to the target, then it becomes very difficult for it to elute out when you are doing the washing or when you are doing the regeneration. So you need to consider this particular point. We do not want too strong a binding, then you need a very strong conditions to unbound whatever has been bound to the ligand. And if you use a very harsh condition, you may deactivate the protein, or the protein may get unfolded, it may lose its activity. So you need to keep that point in mind. So basically you are talking about how strong the binding is so that there is no leakage of the protein vis-a-vis how easy it is to disrupt the protein which has been bound. So you need to play around these two values actually. So leakage of target molecule during sample loading indicates sample residence time is too short for complete binding, okay. So slowly the target molecule is coming out, that means you are not giving enough time for the ligand and the protein to interact. So one way of doing that is we inject little bit, so we are injecting then stopping the flow, then again we are injecting and then stopping the flow, okay. So multiple small injections, that is one approach. Another approach is to decrease the solvent flow rate. Of course the third approach is to modify the system so that the Kd values becomes smaller so that the binding is stronger. But process wise what can we do? We can inject little bit, stop, inject little bit, stop, and so on. So that is one approach. Other approach is to reduce the solvent flow rate, because your residence time is too short, that is why your target molecule is getting leaked out. There is another type of chromatography, that is called immunoaffinity chromatography. This is a modification to affinity chromatography. It is used generally in antibody columns. If you want to purify antigens, for isolating receptors, enzymes and DNA fragments, for removal of toxic components from blood, for large scale preparation of monoclonal antibodies. So for such antibody type of purification we use this immunoaffinity chromatography. So if you want to purify antigens, you want to isolate receptors, enzymes, DNAs, if you want to remove toxic components from blood, that is called hemoperfusion, or if you want to do preparation of monoclonal antibodies, then what do? You use something called the immunoaffinity chromatography. So basically what do? We can produce antibodies for any compound. Then what do? These antibodies are immobilized on a stationary matrix. So we can purify the parent compound. So if there is a mixture which contains your parent compound with other compounds, these antibodies which have been prepared from the parent compound will be very selective towards these parent compound, and it will not bind rest of the compounds. So that way we can achieve very high purity. But this is a very expensive technique, it adds to the purification cost. So if you are interested in preparing very pure components or products like monoclonal antibodies or antigens, or we want a purification of blood where you do not want any toxic compounds present, okay, then this type of technique are adopted. So another affinity chromatography method is incorporating various temporary affinity tags or affinity tails. So we attach a affinity tag and then we perform this affinity chromatography and then we remove the tag, as simple as that. For example, everybody knows his tag. So we attach a his tag onto a protein, okay, then these tag proteins are purified on metal chelate such as nickel in an affinity chromatography column. Then the affinity tag can therefore be used to purify a fusion protein or an immunoaffinity column. Then the native protein can be recovered by cleavage using enterokinase. So we are using an enzyme so that the his tag on the protein gets removed, okay. So initially you attach a histidine tag to the protein and then we use some sort of a nickel affinity column, purify the protein, and then we remove the histidine tag using a enzyme to cleave the attached histidine. Then there is another type of chromatography which is called ion suppression reverse phase chromatography. So the name implies that we are trying to suppress the ionization of a particular protein. Once you suppress, then you use the reverse phase system to purify. So this is very suitable when you have the stationary matrix or the phase is non-polar and the mobile or continuous phase is polar, but under operating conditions may turn non-polar. So what do? We add a pH buffer so that the mobile phase is suppressed of ionization. So by adding a pH buffer, we are preventing the ionization of the solute in the mobile phase, and then we are using a non-polar stationary phase. So what happens? The polar analytes will elute out first, non-polar analyte will elute out later, because your stationary phase is non-polar, that is why you have the reverse phase. So the ion suppression is achieved by adding a pH buffer, so it prevents the ionization of the solute, okay, and then you have a reverse phase stationary phase, so the polar analytes will be coming out first. So if the analyte or the solute is in ionized form, then you are going to have a problem, the separations will not be very good. So by suppressing the ionization, we have now polar non-ionizable product and non-polar material, and the stationary phase is a non-polar or reverse phase material. So the ion suppressed polar material will come out first. So this is called the ion suppression reverse phase chromatography. So in this technique, ionizable compounds are kept in their ion suppressed form. Now ionized compounds are very polar, as you know. So under reverse phase condition they will elute out very quickly from the column, leading to poor separation with respect to the ionized analytes. So if you have many ionized analytes, they will never get separated out at all, they will just come out of the column very fast because they are highly polar. So what do? You suppress the ionization by adding a buffer, then there will be some interaction between the non-ionized polar compounds on the surface, which is reverse phase. So some separations will happen in the various polar analytes. So we are using a buffer and appropriate pH so that the ionization is suppressed. So weak acids and bases may be effectively separated under this reverse phase condition. So the pKa of a molecule can be used to determine the correct pH of the buffer in the mobile phase. So based on the pKa we can adjust the pH in the buffer, okay. So for example, for organic acids such as ethanoic acid, you know pKa is 4.75, so the pH should be kept below its pKa, so we have to use lower pH so that you are preventing the ionization. So if organic bases such as trimethylamine, pKa is 4.19, so the pH is adjusted above its pKa, so we go to higher pH so that it does not get ionized. So by this modification, these weak organic acids and organic bases are efficiently separated in a reverse phase column. Otherwise if we do not suppress the ionization, these acid or these bases will get ionized, and the separation efficiency of these compounds are extremely poor in a reverse phase chromatographic system. So this is called a ion suppression reverse phase chromatography. Okay, now we talked quite a lot about different types of chromatography. We talked about hydrophobic or reverse phase chromatography, we talked about ion exchange chromatography, we talked about the gel permeation or gel filtration chromatography, then we talked about these ligand based affinity chromatography. All these are the basic chromatographies, and there are many modifications to this where we are talking about ion suppression chromatography and so on. Now let us again go back to the mathematics of this column operation and see how we can build up some more relationships between various parameters in the flow. Okay, now we have a long stationary phase and we have the mobile phase travelling over it. Now this stationary phase can be divided into multiple stages. I originally mentioned that in engineering some of the unit operations are viewed as staged process, equilibrium staged process, like adsorption, extraction, distillation, chromatography, all these are considered as equilibrium staged processes. That means you have many fluids, they come in contact with each other, then they at equilibrium they get separated, so the solute concentrations that are leaving the stage are in equilibrium with each other, then they go to the next stage, and again there is a mixing of various fluids, and again the fluids get separated, and the fluids that are leaving each of the stage are in equilibrium, and so on it happens. So by using this type of concept, by using the concept of mass balance, we can build up lot of equations in staged processes, and you can see there is a similarity between many of these stage processes, distillation or adsorption or extraction or chromatography, okay. And we have a mass balance as one of the equation, and we have the isotherm or relationship between the streams leaving out of the stage as another equation, and we can perform many calculations. So that is what we are going to do. So consider a chromatographic column as a stage process. So we have the stationary phase in small stages, they are called like an end stage process. Now we have the mobile phase travelling from one direction to another direction, okay. So the solute gets adsorbed, desorbed based on whatever be the principle. It could be based on hydrophobic interactions, it could be based on ionic interactions, it could be based on affinity interactions and so on, okay. And so we will try to model each one of the stage and extend it to the entire chromatography. That is what we are going to look at, okay. So how do you do the mass balance on each stage? So we, as you can see, we have a stream coming in, stream going out, that is all. In chromatography it is very simple. We have the stationary phase, stationary inside the stage, and what is flow, there is only one single stream coming in, there is another stream going out, okay. Now the stream that is coming in has some solute, and the stream that is going out also has some solute. So accumulation in the liquid because of the material coming in the liquid, and the plus accumulation in the adsorbent. Now this will be equal to the solute inside the stage plus the solute out of the stage, okay. So this is the accumulation, and then whatever is in and whatever is out. So obviously you should have a negative term here because we are talking about out, okay. So material in, material out is equal to accumulation. Now accumulation, there are two types of accumulation. One, the accumulation of the solute in the continuous phase, another is the accumulation of the solute in the stationary phase or the adsorbed phase. So we have the solute coming in because of the stream that is travelling inside minus solute going out because of the stream that is going out, that is equal to the accumulation. Accumulation is of two types, one is accumulation in the liquid, accumulation in the adsorbent. Okay. So when you do that, let us look at a stage n. So whatever is coming in is Q into Cn minus 1, that is the Cn minus 1 is the concentration of the solute entering in from the n minus 1th stage. Cn is the concentration of the solute that is leaving the nth stage. Q is your solvent flow rate. We assume that the solvent flow rate is constant in each of the stages. So Q into Cn minus 1 is the solute coming into the stage, Q into Cn is the solute going out of the stage, there is a minus term. So obviously this is the mass balance. On the left hand side we have the accumulation. There are two types of accumulation I mentioned. One accumulation is related to the accumulation of the solute in the mobile phase, other one is the accumulation of the solute in the stationary phase. Now again let us go to the accumulation in the mobile phase. What is the equation? Epsilon, that is the volume fraction or void space in the stage, into Vs is the volume in single stage. So this could be volume of the entire column divided by n stages. Suppose there are n stages, capital N, single stage volume will be V by n. We have to multiply by the voidage because you have solids also present inside. Okay, so epsilon is your voidage. So E into Vs is the volume of the liquid space inside a stage multiplied by dCn by dt. Okay. So this is the accumulation of the solute in the liquid part inside a stage, plus there is accumulation in the solid part also. So if epsilon is a void space, 1 minus epsilon will be fraction of solids present in a stage multiplied by Vs, Vs is the volume of each stage, into dQn by dt. Q, small qn is the solute concentration in the adsorbent or solute concentration in the stationary phase in that particular stage n. So please note we have Cn, Qn, Cn minus 1. So Cn is the concentration of the solute in the mobile phase inside the stage as well as concentration of the solute in the mobile phase leaving the stage small n. Cn minus 1 is the concentration of the solute in the mobile phase entering the stage small n. Qn is the concentration of the solute in the stationary phase inside stage n. Very straightforward equation. Qcn minus 1 is the concentration of solute entering stage n minus Qcn is the concentration of solute leaving stage n. This is equal to the accumulation. There are two types of accumulation. One accumulation is the concentration of the solute in the mobile phase, other accumulation is the accumulation because of the stationary phase. For stationary phase concentration we use Q, for the mobile phase concentration we use small c. Epsilon is your voidage, Vs is the volume of single stage, that means volume of the entire column divided by n is your number of stages, capital N. So you see we will have many differential equations like this for each one of the stage. So we can have C2 minus C3, here you will have C3, you can have C3 minus C4, here you can have C4 and so on. So for each stage we can have this type of differential equation. Now how do you relate Cn and Qn? We talked a long time back, there could be a linear absorption type of relationship between Cn and Qn. Okay. So Qn, that is the concentration of the solute that is adsorbed, and Cn is the concentration of the solute in the mobile phase, if they are in equilibrium, they are related as a linear isotherm relation. We can have non-linear relationship also, but here we are assuming a linear relation. So, Qn equal to K into Cn, okay. This is a simple relationship. We can have a non-linear type of relationship, we can have a Langmuir type of relationship and so on, but the simplest is the solute that is adsorbed on the stationary phase and the solute that is there in the mobile phase are linearly related. So, by putting in the value for Qn like this, we can rearrange the equation to get a differential equation like this. So, Q into Cn minus 1 is the amount of solute entering stage n, Q into Cn is the amount of solute leaving stage n. This is equal to a big number here dCn by dt. Now, this is called a differential difference equation, because I can have many equations like this for each of the stage. So, stage 1, stage 2, stage 3, stage 4. So, inside stage 1 this will be C1 and this will be feed concentration. Inside stage 2 this will be C2, this will become C1. Inside stage 3 this will become C3, this will become C2, this will become dC3 by dt and so on, okay. So, first stage Cn minus 1 will be Cf, Cf is the feed concentration. So, this is called a differential difference equation, because you are going to have many equations like this. This is differential part, this is difference part. So, there are many techniques to solve it. So, please note that we had considered linear isotherm, that is why we are able to combine all these into single term, okay. If you consider non-linear equations, we cannot solve them analytically, but once you consider a linear isotherm relation, we get a series of differential difference equation, then it is very simple to analytically solve it. So, let us not go too much into the analytical solution procedure, but you need some initial conditions as well. If you want to solve any differential equation, we need initial conditions, okay. So, what happens initially? There is no solute, that means at time less than 0 we have no solute. So, Cn equal to 0 at all n's 1 to n, okay, at time less than 0, where capital N is the number of stages, total number of stages. Now, at time equal to 0 I am injecting the solute, okay. So, at time equal to 0 I am injecting the solute in the beginning, in the start of my in my tubular reactor or tubular chromatographic column. So, these are the initial conditions. So, by using these initial conditions, one can get a relationship for Cn, that is the concentration inside the stage n or the concentration leaving the stage n. This is given by this particular relation, Cn equal to Cf phi raised to the power n minus 1 E minus n divided by n minus 1 factorial, where phi is given by capital N. Capital N is the number of stages, Q into T, Q is the flow rate of the continuous phase divided by epsilon plus 1 minus epsilon k V. So, you see V is the total volume of the chromatographic column, N is the number of stages in the chromatographic column, Q is your flow rate, T is the time, epsilon is your porosity, K is the linear adsorption isotherm, which relates Q and C. So, Qn is equal to K into Cn. So, this equation is very useful. Let us look at our original chromatographic equation, which assumes a Gaussian type of distribution, correct? Okay. Before that, let us go back. When the number of stages is small, the concentration change as a function of time will be an exponentially decaying curve. So, if number of stages are very small, you are going to get, as time goes, we are going to get like equations like this, but as the number of stages become larger and larger, you are going to have a Gaussian type of distribution like this, you know. So, if the stages are very small, if the stages are 1, then you are going to have this type of reduction. If the stages are more than 1, slowly you are going to get, but this is not a uniform Gaussian distribution, but as stages become extremely large you are going to get a uniform Gaussian distribution. And the equation for a Gaussian distribution is what? C equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square. This is the equation for the Gaussian distribution, where T is your time, T naught is this particular thing, okay. That is the time at which you get a maximum in the peak, okay, and then T naught sigma is your standard deviation of this particular relationship. I hope you remember this equation. We talked about this equation many classes back. This is a standard equation for a Gaussian distribution. So T naught is the time at which the maximum of the peak appears, so it is called the elution time. C naught is this maximum concentration, okay. Now so C is a function of 3 variables, T naught, sigma and C naught, and standard deviation is given by T naught sigma. So by comparing this relationship, okay, with the previous relationship which we prepared or which we derived for a discrete stage model, we can say that sigma square is equal to 1 by n. So you see that there is a relationship between sigma and number of theoretical stages or theoretical plates. And what is sigma? T naught sigma is the standard deviation, okay. So if I know the standard deviation, I can calculate what is the number of theoretical stages in of a column. So what do? I inject a sample and I see the T naught, okay. T naught is the time at which the elution is maximum, then I get the standard deviation of the Gaussian curve. Then what do? From this equation I can calculate sigma, and then from this equation I can calculate n, that is the number of theoretical stages or number of theoretical plates of the column. So it tells you how efficient the column is going to be. That means it tells you the total number of stages in that particular column, okay. So this is going to be a very useful equation. We will look at some problems related to this equation. Now C naught, that is the concentration maximum, will be a function of the feed concentration and the number of theoretical stages in this fashion, okay. So again if I know Cf, that is the feed concentration, and if I know the number of theoretical stages, I can tell what will be the maximum concentration of that particular peak that is going to elute out. So you see these equations are very useful for doing plenty of calculations. We are going to look at it as time progresses. And then T naught, that is the elution time, that is the time at which the peak is maximum, is related to your voidage, it is related to your linear adsorption isotherm term K, volume of the bed and height of the bed, okay, this fashion. So by substituting all this into our Gaussian relation, we get C is equal to, here in a Gaussian relation if you remember we had C naught is Cf by square root of 2 pi n exponent of minus T by T naught minus 1, here we had sigma square. So we have 2 by n, n is the number of theoretical stages or number of theoretical plates. Now instead of T naught elution time we can also use elution volume, that is instead of T we can substitute as V. So we get V by V naught. V naught is the maximum elution volume, the volume at which you get the maximum in that peak. So these two equations are very useful. Here we have the number of theoretical stages, we have the feed concentrations, we have the elution time coming into the picture, and here we have the concentration coming on the left hand side. So these equations again can be used for design calculations, as we are going to see some more problems as we go along. Now let us look at a problem. Imagine I am injecting a solute at time equal to 0, and at 10th minute I get this peak maximum, we will assume this to be a Gaussian distribution. So T naught will be 10 minutes. Now the standard deviation is 0.5 minutes. So what is the number of theoretical stages or number of theoretical plates for that particular chromatography? So which equation do we use? So we can use that the equation which connects sigma with n. So what is the equation? Standard deviation equals T naught sigma. So here T naught is given here 10 minutes, standard deviation is given here 0.5. So I can calculate sigma. Okay, once I calculate sigma, then I use another equation which is relating sigma and the number of stages. What is the equation? Sigma square equal to 1 by n. So n is equal to, from sigma I take n is equal to 1 by 0.05 square. So n is equal to 400. So it means this particular chromatographic column has 400 stages. So you see, if your sigma is smaller, your number of theoretical plates is larger. So if sigma has to be smaller, then your standard deviation also has to be smaller. That means if the curve is very broad, your theoretical plates are very small. If the curve is very sharp, your standard deviation is low, then sigma is low, then number of theoretical plates will be large. So when I inject a sample and I get a beautiful sharp curve, then I can be sure the theoretical stages are large. If I am getting a broad curve, then I can be sure my theoretical stages are less. So you see, by looking at the shape of the curve that is eluting out, we can tell what type of column it is, how effective the column is. Does it have large number of stages or does it have small number of stages? So if you are buying a packed column from a vendor, we generally ask how many stages does it have. Does it have 400 stages, 500 stages, 1000 stages, 2000 stages. So by looking at what the vendor is saying, and when we know the number of theoretical stage, we will be able to tell what will be the width of this particular peak. Why is it important? Suppose I have two curves, and if the width is very small, the suppression will be good. If the width is very broad, you are going to have an overlap of one curve with another. That means there is going to be an overlap of one solute with another. So you are going to produce large amount of mixed solute. So this problem tells you how efficient this particular column is based on the elution time and based on the standard deviation. Let us look at another problem. This is in a different way. So we know the elution time, it is 85 minutes, the width at half maximum, that is this place where the maximum is half. So if you assume the overall height of the particular peak is h, at half h, if this width is given, that is 5 minutes, can you calculate the number of theoretical stages? So this width is given. In the previous problem, T naught is given and standard deviation is given, you are asked to calculate the number of theoretical stages. In this particular problem, the T naught is given, width at half the maximum is given, you are asked to calculate theoretical stages. So how do you do this? Think, how do you do this problem? We need to use the C equation, okay. So we can use this particular equation, C is equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square, okay. T naught is known, okay, sigma we do not know, but then we can substitute sigma square is equal to 1 by n, right. So by substituting this, if we know all these, we can calculate n, okay. Now C by C naught is half at these places, C by C naught is half, correct. At this place C by C naught is 1, okay, and this is 5 minutes. So obviously this place is 85 plus 5 by 2, that is 87.5. So at this place the concentration C divided by C naught will be 0.5 at this place, C by C naught is 0.5 and the time will be 87.5 minutes because this is 85 minutes and this width is 5 minutes. So obviously this is 5 by 2 plus 85, 87.5. So the time here is 87.5 and T naught is 85, C by C naught is 0.5, so only unknown is n. So you can calculate the number of theoretical stages. So T is equal to 85 plus 5 by 2 as I said, your C by C naught is 0.5, so everything is known except your number of stages. So we can calculate from this relationship the number of stages comes out to be 1600. Okay. So in this problem what we did, we know the width at half the maximum, okay, the time, then we tried to calculate the number of stages. So we used this particular relationship. So you remember we used to have sigma square here, sigma square is equal to 1 by n. So we are using C is equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 into 1 by n. We know T naught which is 85, T is 85 plus 5 by 2, C by C naught is 0.5. So we substitute everything, the only unknown here is n, so we can calculate the n. So it is very straightforward. So you see we did two problems, both calculating the number of theoretical stages, both is based on a simple experimental procedure. So what you do, you inject your solute at time equal to 0 and see when the solute is coming out or eluting out, you know the time. If you know the width at half maximum, also we can calculate the number of theoretical stages using this particular relationship, or if you know the standard deviation, we know that sigma T0 is equal to standard deviation. So from there we can calculate sigma, and as you know sigma square is equal to 1 by n, so we can get the value of n. So both the ways we can calculate the number of theoretical stages or number of theoretical plates. Why is it so important? This number of theoretical stages or number of theoretical plates is very important because it tells you the quality of the chromatographic column. Higher the stages, that means better will be the resolution and better will be the separations, and sharper will be the peak. So the Gaussian peak will have a very good sharp appearance. So if you have multiple solutes present, the overlap of these solutes will be minimal. So that is the main advantage. So we need to know the number of theoretical stages. Even if we are purchasing a column, we always tell give me a column with so many theoretical stages. So we can substitute the theoretical stages into our equation and tell how good these separations of various solutes are going to be, or how sharp the peak is going to be. So the main assumption in this equation is the peak that is getting eluted out of my column is a Gaussian distribution, that means it is an uniformly looking curve. So we make use of the mathematical representation of a Gaussian relationship. And what does a Gaussian relationship look like? It is like this: C is equal to C naught exponent minus T by T naught minus 1 square into 2 sigma square. That is how a Gaussian distribution is going to look like actually. Okay. So making use of that relation, we can do several calculations, and also by making use of the discrete stage analysis, we are able to develop, just based on mass balance, develop relationship between the solute concentration going in and the solute concentration going out, and equate it to the accumulation. And if you assume a linear adsorption relationship, we can get quite simple relationship between various parameters, which can be used for all these type of analysis. Now we will continue further in this mathematical analysis, and how do you make use of these mathematical equations for designing columns, looking at performance of columns and so on. So we will continue them in our next class.